All right, so just talking about resonance. I'll start off general talking about resonance. Some common things that came up were basically how do we know when to stop? I will tell you. I will say give 2 examples, right? Or I'll say give 3. I won't say draw resonance structures, right? Otherwise, you don't know how many to draw. I'll always be very specific. So the question is how to know when to stop. Really careful reading of our directions will be the key. That's part of the reason why I make you do sapling. It actually is sapling makes you really read directions. And if you don't read the directions very carefully, it won't work. You'll get the wrong answers, right? So it's really practicing reading the right things. One piece of advice you could do is redraw the first structure, right? So redraw the first structure. So if you want to do a resonance form, let's say I was doing, when we did in class, we did this in class. I think we had something like this, or I've done one like this. All right, if you had something like this, first I would always number atoms. I think it's important to number atoms. Maybe not the hydrogens, but certainly the atoms. So 1, 2, 3, 4, 5, 6, 7. Loop those electrons, come down, make a pi bond, break the pi bond between 2 and 3. That lone pair goes to carbon. The pi bond electrons go to carbon 3. We draw a resonance arrow. Things that didn't change. Right? So there should be a lone pair now on that one, a pi bond here, and we'll see 1, 2, 3, 4, 5, 6, 7. And of course I'm missing something. What am I missing?
Plus on the nitrogen.
Plus on the nitrogen. Yeah, balance that charge, right? So you could keep drawing. You could certainly keep drawing from this structure if you wanted to, but sometimes it's easier just to redraw this and start again if you want to. You don't have to. So we could just, redraw this just like it was before. Drawing in those lone pairs. 1, 2, 3, 4, 5, 6, 7. Come down. And this time we could have these form a new pi bond. And these go to stop at 5. And now that negative charge, the extra electron lone pair, would be on carbon 5. So we formed a new pi bond between 1 and 2, a new pi bond between 3 and 4. Plus charge, minus charge. Number those atoms, 1, 2, 3, 4, 5, 6, 7. And the neat thing is we can get to the same resonance structure if we didn't want to redraw it, so I redrew it. If I didn't want to redraw it, I could also do it from this. And that gets you here as well. Right, so that gets you there as well. So taking a look at workshop on the nomenclature and the intermolecular forces, we're looking at 2D. And the question is, which is going to have a higher boiling point or melting point? And that, it doesn't really matter. And the answer I wrote is this one, because of the size and the another way of saying the polarizability of the iodide, large atom, right? Of course, how I come up to this is because I'm looking at, chlorine versus iodine. And I look at where chlorine and iodine are in relation to each other on the periodic table. So it goes fluorine, chlorine, bromine, iodine. They're in the same column. And I've told you as you go down a column, size increases, which means polarizability increases. Now, I've told you all that as you go down a column, size is the most important factor. And as you go across a row, electronegativity is the most important factor. But does size change as you go across a row? Yes. Does electronegativity change as you go down a column? Yes. So if you were to write here, but I think the most important thing as you go down a column is size. So the question is, well, wait a second, chlorine's more electronegative than iodine. Is that going to be a more polar bond? Not really. Well, it's not the most important factor. That is true. Chlorine is more electronegative than iodine. Not false statement. It's just not the most important factor here when you're going down a column. It's going to be the size and polarizability, right? Orbital overlap, the bond there is going to be just that's the bigger factor. Okay, so looking at a problem about major and minor resonance contributors. And we're looking at homework number 2. So it's 26 in somebody's homework. So everybody's 26 is not the same, but some of you have similar problems. It depends. But the question is, identify the major and minor resonance contributors for the formate anion. So it's HCO2 minus. And they have it drawn out for you. They have it drawn out like this. All right, so we're going to take we'll make it a little more challenging than the one that was on sapling. So let's draw some resonance structures here for this. So first thing we're going to do, we should number 1, 2, 3. We'll number hydrogen this time 4. Why not? So this oxygen has a negative charge, has 3 lone pairs. What's the hybridization state of this oxygen right here? Oxygen 3. What's this hybridization state?
SP3. SP3.
It's SP2. Remember, right? If this oxygen wasn't next to another pi bond, it would be SP3. You're right, but it is next to an extra pi bond. That means it's able to do resonance. If you're able to do resonance, the only way you can do resonance is you have to have a p orbital. Does SP3 hybridize have any p orbitals? No. So it can't be SP3 hybridized. It has to be SP2 hybridized. Which means one of these lone pairs needs to be in what hybrid orbital? P. And that's the one that's going to do resonance. Right? So that's the electrons we're going to move. And we're going to break that pi bond there. And if you're going to break a pi bond, which of course is made up of what kind of hybrid orbitals? Pi bonds are made up of p orbitals. You have to have a p orbital, right? So what does that result in? Let's see. Sometimes resonance structures actually help us see this, right? If you draw this resonance structure now, and you look at this, 1, 2, 3, 4. Right? If you look at that now, you're like, oh, of course, oxygen 3 is sp2 hybridized, right? So sometimes resonance structures help us see these things, actually. Right? What else could we do? Nothing really, as far as I'm concerned. They do a weird one. There's one weird one that's legal, but it's not great. What is it?
Incomplete octet on the
Yeah, like break this pi bond, have those 2 electrons go to that oxygen, and that would give a couple reasons why this isn't great. Number atoms, 1, 2, 3, 4. So why is this one not a great? Why is, if I label these A, B, C resonance structures, why is C not great?
incomplete octet.
Octet rule is the best reason why it's not great. Carbon wants 4 bonds. That's an octet rule question. Yep, absolutely. Yep. So we're just saying this isn't great because this carbon doesn't have a full octet. So that's octet rule is the most important rule. What's another reason why this isn't great? C.
Formal charges.
More. What about formal charges? There's too many of them. There's more formal charges than you need, right? So that's not great. So which one of these is the least likely resonance contributor? A, B, or C? C would be the minor one. And what about A and B? Which one of those is better? They're equal.
They're equal majors.
They're equals. Yeah, they're both majors. Yep. The question was a little bit different in the way they did it, but that gets you to the heart, I think, of what we're trying to think about here. So just to clarify, major and minor would mean major would be the most likely one, right? The major contributor, right? That's all it is. So, but remember, this isn't a reaction, right? Resonance structures aren't reactions. It's not like a major product. It's a major contributor, right? So it's not a reaction. Major or minor just means more likely or less likely. Good question. All right, so we've made up a chair here. The folks here came up with. So we're going to turn this into we made a cyclohexane ring with two wedges, right? Which mean they're coming out at us. Or another way to look at this is the OH and this propyl are on the same side of the ring, right? So we can say this time they're both on the top. Let's look at it that way. So let's draw a chair. It doesn't matter which chair I draw. I could draw this one, or this one. I could draw that one, or I could draw that one. It doesn't matter as long as what happens. What never changes. If you're up, you're always up. If you're down, you're always down. Right? So it actually doesn't even matter if I draw these up on the chairs. I mean, you can always draw them up, I think. But the OH and the propyl need to be on the same side. That's all. So if I do make it easy on myself, and also, does it matter which of these carbons I decide to make carbon number 1? No. Doesn't. But I like to make it easy on myself. Sometimes just make the top part of the chair, the head of the chair, always number 1. Just easier to see. So 1, 2, 3, 4, 5, 6. So let's say there's a ring flip in here. Actually, that's not true. I take that back. That's not a ring flip. I'm just drawing two chairs the other way. Carbon 1 is up. So that's the OH. Is that going to be axial or equatorial? The up position on carbon 1 is axial on both, actually. So all I'm showing here is that you could have drawn it either way. The chair could be leaning to the right, chair could be leaning to the left. It doesn't matter. Either one's right. So if the OH is up, on carbon 3, there is the what? The propane. Is that going to be in the axial position or equatorial position? So if you look at carbon 3, let's look at here. Well, let's think. It goes every other one, right? So carbon 1 has axial up. Carbon 2 would have axial down. Carbon 3 would have axial up. It goes every other one. Right? Axial up on carbon 1. Axial down on carbon 2. Axial up on carbon 3. Axial down on carbon 4. Axial up on carbon 5. Axial down on carbon 6. Right? The axial and equatorial positions switch every time between carbons, every other carbon. Yes? So this is, if it's going to be on the same side, if it needs to be up, it needs to be up like that, the axial position. 1, 2, 3 carbons. 1, 2, 3 carbons. Over here, it'd be up as well. Like that. All right, so let's take this another level. So this is what we're working with. What if we wanted to do a ring flip for either of these? All right, what if we wanted to do a ring flip for these? Or not. All right, so if you do a flip, number 1 here is going to be pulled down, number 4 is going to be pulled up. So your ring would go the other way. If it's leaning towards the right here, after the flip, it's going to be leaning towards the left. This one's leaning towards the left. After the flip, it's going to be leaning towards the right. All right, so what would that look like? First, we need to practice drawing it. So if it was leaning towards the right in this first one, now we need to have it lean towards the left. Renumber those carbons. So this is 1, 2, 3, 4, 5, 6, right? Carbon 1 got pulled down, carbon 4 got pulled up, and everything else is moved over accordingly, right? Everything else moved over just accordingly. 1 got pulled down, 4 got pulled up. Do the other side. Now it's leaning towards the right. One got pulled down, 4 got pulled up, 1 pulled down, 4 pulled up. Now we add in the things like we did this last time. So the OH and the propyl were both up. Are they still going to be up? Yes. And the first one, they were both axial though, right? Are they going to stay axial? No. Now they're going to be equatorial. So after a ring flip, if you're axial, become equatorial. If you're equatorial, you become axial after ring flips. But if you're up, you're always up. If you're down, you're always down. So let's just make sure we draw it right. So 1 up position is equatorial. That's an OH. Makes sense. 3 for that propyl is up, equatorial. OH. Up with the propyl. So yeah, so just to reaffirm, right? Axial means kind of this up or down positions, right? So this is an axial position now in carbon 3, right? So it's equatorial down before. This H. Axial just means kind of in the axis of the board, like anything, right? Right, the axis is here, the equator is this way. That's all it's saying. Yeah.
And so when it's equatorial, the way that you know which way it goes, which way the chair is leaning, right? So it's going to be the opposite way.
No, be careful. Right. So I like to divide the ring in half, and then once you divide it in half, everything on the right points to the right, everything on the left points to the left in the equatorial positions. Right. So like if you divide this in half, it goes that way, this way. Yeah. Who can think of which ones do you think is more stable? Things in axial positions or things in equatorial positions? What do you all think is going to be more stable? And why? Why? 50-50 shot, you had a guess. That's a good guess. That's the right answer. Why might that be?
Wait. Things in the equatorial are more stable.
Yes.
Yes.
Why?
Because of 1-3 something interactions with the hydrogens.
So what does that mean?
I don't know.
Axials are more stable just because things are farther away from each other, right? What have you guys been learning about? Electrons are in bonds, right? Which bonds are farther away? Things are pointing away. This makes it more stable. We'll talk more about that on Monday after the quiz. So a question is, how do you even start these things sometimes, right? It's just hard to start. And I know I said this in class, is find the head, find the top part of the chair, whether it's leaning right or leaning left. Find that head, and that always has axial up. Right? Or you can find the feet, and that's always axial down. But find that spot, and then that you can do everything else. From that, once you know that one, you can do everything else. So find either the head, and that's axial up, or find the feet, and that's axial down, and then go from there. You got everything. So taking a look at that first workshop, workshop number 1, in the bonus question, and just going to think about hybridization state with this. It's how we relate hybridization state and what can do resonance and how that affects what hybridization state you'll be. So the first thing we asked about hybridization state was, what kind of bonds do you have, right? And that helped us answer a lot of things, right? If you only had sigma bonds, you'd probably be sp3 hybridized, right? If you had 1 pi bond, you're sp2. If you have 2 pi bonds, you're sp. the resonance part threw a loop to that, right? Resonance added another complexity to that because resonance does what? What does resonance do? What's the point of resonance? Why does resonance happen? Look in your notes. I gave you a definition in your notes. The right-hand side of the board, it was in red in the second part, and black in the first part in hour 1. This first in the second hour, it was just black.
Spread out charge to stabilize it.
Spreads out charge, and that's good because it stabilizes molecules. It makes molecules stabilize. So resonance, right? Hybridization state will change if you can do resonance because it helps stabilize molecules. So let's look at these examples. So let's go A, B, C, D. So in A, let's look at the oxygen. What's going to be the hybridization state of that oxygen? sp2. That's correct. It wants to have a p orbital, a lone pair in that p orbital that can do resonance because it's next to a pi bond. Good. What about B? What's the hybridization state of that oxygen? sp3. Right? Notice there's another sp3 hybridized atom here. This lone pair is not next to that other pi bond. It can't do resonance, right? We can't do resonance through sp3, right? sp3 atoms don't do resonance. Right? We can't break sigma bonds.
How they do it again?
But no, so I could. Here we go. 1, 2, 3. 1, 2, 3, 4. Carbon 2 is what hybridization state? sp3. Can sp3, right? Carbon 2 in this one right here in B. Carbon 2 here is sp3 hybridized. Can sp3 hybridized atoms do can they do resonance? No. So this oxygen is going to be sp3 because it can't do resonance. Right? Normally it'd be sp3 if it can, unless resonance, right? Because resonance stabilizes molecules. Right? So this oxygen is sp3 hybridized because only sigma bonds, and it can't do resonance. This oxygen also has only sigma bonds, but it's choosing to be sp2 hybridized so that one of these lone pairs can be in a p orbital so it can do resonance. Yep, and then this can't do resonance because carbon 2 here has only sigma bonds. It doesn't have a pi bond. So it can't be part of the resonance. So this lone pair can't do resonance. So then, all things being equal, it'll just decide to be sp3 hybridized, that oxygen. Now, what about C? What's the hybridization state? Let me number these carbons for you. 1, 2, 3, 4, 5. For C, what's the hybridization state of carbon 3? Hybridization state will be sp2, that's correct. It's going to have a p orbital, and what's in that p orbital? What's in this? Plus charge isn't a thing, it's just empty. Right? We draw the plus charges like holes. So carbon 3 here is sp2 hybridized because it's a carbocation, and we talked about those bond angles. If you look at your class notes, the top of those class notes, about 90 and 120. It's there, right? It's going to be sp2 hybridized, have an empty p orbital, so it can do resonance. What about D? What's going on in D? 1, 2, 3, 4, 5. What about carbon 4? What's the hybridization state of carbon 4 going to be?
I think SP3.
Look at your class notes. Carbon 4, right? Carbocations are always sp2 hybridized. Woo! Always, right? Because that gives us the geometry, right? That gives us the geometry of the empty p orbitals as close to those bonds as possible. Carbocations are always sp2. Carbanions can be sp2 or sp3. They'd like to be sp3 unless they can do resonance. Right? Resonance is the key. Resonance is the key. Look for that resonance. So another example. Give you another one. Well, these two. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. For E and F. For E, carbon 3 has a negative charge. What's its hybridization state? sp2, right? Why? Because it has that lone pair. It's going to want to put it in a p orbital so it can do resonance with carbon 2. So this one's going to be sp2 hybridized. And that lone pair is going to be in a p orbital. Remember, you'll box hybridization states. I won't box the hybrid orbitals.
Wait, so for resonance on that one, would the pair from the pi bond go on to carbon 1 and then the lone pairs go on, make the bond between 2 and 3?
Right. So if I drew that resonance structure, it would be like this. I'd form a new pi bond between 2 and 3, and the electrons in the pi bond between 1 and 2 would go to carbon 1. So that would look like one, 2, 3, 4, 5. That'd be the resonance structure there. Good question. What about F? What's the hybridization state of carbon 4 with the negative charge? Can it do resonance? No. If it can't do resonance, a carbanion has electrons. We want to get those electrons as far away from each other as possible. What geometry gets electrons as far away from each other as possible?
sp3.
sp3, 109.5. I know sp2 and sp have the 180, 120, but it has another bond angle too, doesn't it? What's that other bond angle with those? It has those 90-degree bond angles as well we always forget about. So that'd be sp3 hybridized. And can it do resonance? Can F do any resonance? With that, at least that lone pair can't? Can it? Nope. Good.